Hey, what's up, guys? Pardon me. A few days ago, I watched the video from Julian Eilert, one of my favorite YouTubers, where he was making some one-to-one transformers. And he touched a little bit on transformer theory, but not so much. And his transformers were only one-to-one. They weren't so much transformers as they were isolation jokes. So I thought I could get a little bit more into it. So I just wound a little toroid transformer here, 10 turns on the primary, 20 turns on the secondary. And one of the things that were mentioned in his video were about how you had to use sine waves. Well, that's not true. The only really requirement is that you're using AC. You can't transform DC. It has to be alternating current. So let's take a look here at the scope. All right, I'm feeding in a sine wave at 1 kilohertz, 1 volt, peak to peak. And what you see here is our frequency. Best to look down here at the hardware frequency counter. Most scopes have a hardware counter and a software counter. Your hardware counter is going to be the most accurate. So you see our frequency remains unchanged at 1 kilohertz. And our peak to peak voltage is 1.4 volts. So we have some gain. Now, what you might say is, well, you have 10 turns on the primary and 20 turns on the secondary. Shouldn't there be a 2-to-1 gain instead of a 1.4-to-1 gain? Well, ideally, yes, there should. But this is not an ideal world. This is the real world where there are losses and there is no such thing as a perfect signal. And that's also why we're not seeing a perfect sine wave here on the output. So let me see if I can make it a little more stable. No, not too much. Okay, so anyway, that's a sine wave. Let's see what happens when we put a square wave into it. Okay, so there we have a square wave. Now look at the shape of the wave, but pay more attention to this. 4.4 volts peak to peak. So now we have a 4-to-1 gain. The sine wave is actually more efficient going through this little toroidal transformer. What about a triangle wave? Well, the triangle wave is basically just a geometric sine wave, so it's going to behave pretty much like the square wave. I mean, the sine wave. There's a ramp. And you can see again, we have some gain. That's a negative ramp. Again, we have gain. This is a triangle square. Again, we have gain. This is a stair step. Negative stair step. This is a positive exponential wave. And again, you can see in this type of toroidal transformer, these are all more efficient than a simple sine wave put through a transformer. What does it mean? Well, what it means is there is a great deal of engineering that goes into designing linear and switch mode power supplies. And that is one of the things that I did when I worked for the Bear Corporation. I did a lot of power supply work. And we had standard designs that we went from, but we also were encouraged to experiment to make things more efficient. So instead of our sine wave, when I built switch mode power supplies, I tended to use square waves because I found that when we were making our own transformers, which we did not do except for prototyping, I got more gain. So, not that Julian's video is wrong. Julian's video is full of excellent information. Julian's a fantastic electrical engineer. And I'm not trying to refute it or dispute it. I'm simply adding some information to it. The type of waves do make a difference, but there is no lock that you can't use this type of wave. The only prohibition is it needs to be an AC waveform. So that's it for this little video. I hope you guys enjoyed it. If you did, please give me a thumbs up. Feel free to comment, share, and don't forget to subscribe. Big thanks to all my patrons. That's it. I'm out. Peace.